All right, let's begin.
Our last Weierstrass substitution example. So, how do we do this using Weierstrass? Yeah.
So you know secant x is just 1 over cosine x. So using the substitution, it would just be 1 plus u squared over 1 minus u squared.
Right. So, remember in Weierstrass, our dx is going to become what?
Dx
Yeah.
is 2 over 1 plus u squared du.
And our cosine of x would be 1 minus u squared over 1 plus u squared. So with those substitutions, I'm going to plug these in. You have the 1 over cosine, so you kind of flip these. So it is going to be the integral of 1 plus u squared over 1 minus u squared times 2 over 1 plus u squared. And so those are going to cancel. So just need to be able to solve that integral. How do you solve that integral? Yeah.
You could use partial fractions for that. You could factor the denominator to 1 plus u, 1 minus u. And then from there you can calculate the arbitrary constants by using the cover-up method.
Okay. What's above this one?
One.
This one. And then this one?
One.
It's also a 1 again. It's a positive 1. And so, what do we have here?
ln of absolute value 1 minus u plus ln of plus u.
And our u is going to be tangent inverse, not tangent inverse, tangent of x over 2 plus ln of 1 plus tangent x over 2. Right? So that's the integral of secant without any mysterious multiplying and dividing by this random thing that no one knows how the first guy came up with it, even came up with it. Like, why would you multiply by secant plus tangent over secant plus tangent? Like, where did that come from? So this is a more direct, constructive way of actually getting to this. Right as 1 over cosine, you'd realize here, with the substitution I'm out of luck because if I made the u equals cosine, which is the obvious choice, I don't have any sine of x's to help me out. So substitution is not going to work. Can't really simplify that to work out anything else. Don't really have any basic rules for this thing. So, because it's a rational trig function, Weierstrass. Apply the Weierstrass substitution, you'll get a partial fractions thing, that's your answer. Yeah.
When we found the integral of secant before, like
Yeah.
a couple of weeks ago, we found that it was ln of secant plus tangent, right?
Yes.
Okay. So that's equal to this?
Yes. In fact, I believe that was the follow-up question, right? Show that this answer is equivalent to the one before. So somehow that's equivalent to the answer of ln of secant plus tangent. Does anyone see how?
I mean, what happens if you use the rule where it's like that's equal to the ln of both those quantities multiplied to each other?
Okay, so if you take the ln of the multiplication, right, so that's equivalent to that. Of course, there's a plus c, but forget about the plus c. Where would you go from there? That's a difference of squares. So this is actually 1 minus tangent squared of x over 2.
Oh, that's trig identity.
Trig identity.
Is it?
No, it would have to be 1 plus 10.
1 plus tangent squared is the trig identity. What would this become?
1 over 10 squared. Second.
do here? Yeah?
Could you change tan squared x to secant squared x minus 1?
So that would be secant squared of x over 2 plus 1 at the end of the day. So we have 2 minus secant squared. How do we get that to look like secant x plus tangent x?
You should just secant squared to 1 over. Actually, never mind.
Well, you have to change x over 2 to x somehow, right?
Sure, yeah. But how? Is it true that like 2 minus secant squared x happens to be exactly the same as secant x plus tangent x? How would you even go about proving that? Maybe even getting the cosines in, I probably would have put in the sine and the cosine here, but this is 1 over cosine squared of x over 2, right? Now we know how to rewrite cosine squared as something else.
Yeah. It's
That's gonna double the angle, what's that?
1/2. So I'm just calling it 1 plus cosine 2x.
That's gonna, right, but in this case, the 2x is just x, right? So now we get the angle to be x. So this is in fact, there are nicer ways to do this, but I think this one is gonna work out anyway. Let's just keep running with that. We can combine these. So this is going to be 2 plus 2 cosine x minus 2 over 1 plus cosine x. Things I wanted secant plus tangent. The tangent, to get the tangent is going to give me a sine. I would want to have like a sine squared over a sine over cosine. I would have probably changed this to sine over cosine, just to get that multiplying and combine that. So get back a sine from this is going to be annoying. It's doable, but it's going to be annoying. You could.
Oh, could you multiply the conjugate?
You can multiply by 1 minus cosine x over 1 minus. So this is 2 cosine x times 1 minus cosine x over 1 minus cosine squared x, which you know is going to be a sine squared x.
How?
And then you can split it up and then that's kind of it, no?
No, because it'd be arc.
Right, because this is going to be cosine. This is going to be a sine squared.
Oh, right, exactly.
Anyway, I think we kind of moved away from the answer with that step. I wouldn't have done that step probably. So actually try it from this step. Do it. It's a good exercise. I actually don't want to waste time about that. What I want to talk about now, so do it. There's a way to prove that this answer is equivalent to the other answer. You should should be able to go from this one to this ln of secant x plus tangent x. What I want to talk about now is, because I've actually taught you guys all the techniques that I wanted to teach you, now I just want you to know, how are you going to look at them? Strategy for integration. Right? So you're faced with some random integral. F of x dx. How do you go about computing it? So on test one of the problems is just going to be me asking you, I'm just going to give you a bunch of integrals and say, compute all these integrals, right? So like maybe even problem 1, parts A, B, C, D. Do these 4 integrals, just do them, right? And no hints, no nothing, just like do these integrals, compute, right? So you have some random integral. How do you know how to approach this integral? What method are you going to use, etc., right? So the first 3 steps we've already mentioned, those aren't going to change. Step 1, try to apply a basic rule. And at this point we have a bunch of basic rules. So this is talking about, okay, does it look like x to the n? Because we know how to deal with that. Right, as long as your n is not minus 1. Does it look like 1 over x? We know how to deal with that. It's ln of absolute value of x. Does it look like a sine of x? We know how to deal with that. That's minus cosine of x plus c. Is it a secant? Well, we know how to deal with that. That's ln of secant x plus tangent x plus c, etc. Right? So the integral 1 over 1 plus x squared tan inverse of x plus c, etc. Right? You know a bunch of these rules in your head that you have memorized. So you're pretty much going to see, do any of these rules just apply right off the bat? Like just looking at this thing, can I just use one of these guys right away? It's always going to be the first thing you look for. Now, of course, in a class like Calculus 2, probably not going to be the case, right? Maybe in Calc 1, step 1 is going to work out most of the time. Some of the time, even in Calc 1, we don't really do that. But that's kind of the first thing. Does this look like some basic rule that I know? That may or may not work. Step 2 would be to try to simplify so you can apply a basic rule. So that's if, I think I gave an example of this a long time ago. X cubed plus 2x minus 4 over 4x to the 4th or whatever. Right? So we see some random integral like that. Does it look like a basic rule? Does it look like one of these guys? No. But can I just use algebra to simplify it? The answer is yes, because you have one thing in the denominator. You can actually just divide each thing over here, minus. So that's pretty much just 1 over 4x plus, well, 1 over x cubed minus, well, 1 over x to the 4th. And each of those actually look like a basic rule, right? So this is just the 1/4 times 1 over x plus x to the minus 3 minus x to the minus 4. And then each of these guys, well, these two guys looks like that basic rule, and the first guy looks like this basic rule. So that's just going to be 1 over 4 ln absolute value of x. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. That's going to be a plus 3, and that's your answer right there. So sometimes you're given an integral and it looks really complicated, but you can like simplify it. You can factor and cancel, you can divide something into each term, and it breaks it down to something a lot simpler. Right? So tend to be the second thing that you want to actually think about doing. Is it a basic rule? No. Can I simplify it to make it a basic rule? That's your next thing. Sometimes that's going to work out, but sometimes it's not going to work out. So what would you do if that doesn't work out? 3, try a substitution. Substitution is always the third thing, right? So that's one of the more sophisticated integration techniques, but it is the simplest of the sophisticated integration techniques. If that one works out, chances are it's going to be easier to do it that way than to use any of the other techniques that we actually looked at before. So just try a substitution. And you know all about substitutions, I'm not going to describe that, but one thing that is different now than was in Calculus 1, just note you may not see the derivative of your u in the function as in Calc 1, but try to get it to work anyway. Right? So probably what this, an example here, which probably isn't the best example because you're actually going to need something else, like a to the square root of x. You see something like that, and it definitely reminds you of a basic rule. We do know the integral of e to the x dx. It's e to the x plus c. We have a variation of that, e to the kx dx is 1 over k e to the kx plus c. So it kind of reminds you of this rule, but it is very different because the power, there's a radical x, whereas the power we're used to is a linear power. It's either x or some constant times x. So doesn't really fit. So what we might try to do is, you know what, the radical power is making it things complicated, so probably a substitution for the power. So you do something like t equals the square root of x, right? So that this thing looks like x to the t, e to the t. At that point, you'd have your t squared is equal to x, so your 2t dt is equal to your dx. And so this integral becomes a little more manageable in this form, which at that point you'll know to try like integration by parts or something else, right? But it's a lot easier to contemplate what to do as opposed to what you had before. So you always try to do a substitution. The goal of your substitution is to try as much as possible to get things to look like these basic rules. Now, whether or not you see the du apparent, don't worry about it, you can usually solve for it, right? So there were other situations like if you had x cubed over the square root of 1 minus x squared, right? Technically, if you let like your u or u squared equals 1 minus x squared, what would happen is you'd have your 2u du equal minus 2x dx. So now you have x dx, but you have more than it, so you know, the idea here was to break that up. So sometimes you might have to do a little bit of work to get your substitution to work, but at the end of the day, this would become, your x squared you can solve for from your original substitution equation. That's going to be 1 minus u squared. That's going to be over u. And this is going to be u du. Right? And then you get a very easy integral to do from that. Right? So you might have to do a little algebra to get your substitution to work out, but it will be worth it at the end of the day. Right? So that's always like the third thing. Try to get a substitution in there. Even though it might not be obvious at first, just try it. Right? Figure out what's making this thing complicated. The radical x makes this complicated. Replace it with a single variable. The square root of 1 minus x squared makes that complicated. Replace it with a single variable, etc. Right? So you try to substitute something that makes it easier, makes it look more like a basic rule, and just kind of see where the chips fall. Figure out what your dx is after some algebraic manipulation sometimes. Right? But that's always the third thing you're going to think about. So you see a random integral, no warning, no hints, no nothing. Is it a basic rule? Can I simplify it? Can a substitution work? First 3 questions you always ask yourself. Right? Now, after that point, things get a little sketchy. Right? So these steps that I just mentioned, pretty much in order all the time. Always the first 3 things you think about in this order. The following steps, though, no particular order. So you are faced with an integral where you thought those three things, right? And it didn't work out. It didn't help you finish that integral. Something was off that couldn't allow you to finish off with these guys. Then a fourth option is integration by parts. Right? So now, you know that integration by parts is an option. It's something that's out there, it's a technique. Why would you choose this technique? What would you have to see to know, you know what, integration by parts might be a good idea? It's particularly useful in two situations. There might be others, but these are two that would stand out. One situation is you have a product of two, you have a product of two different kinds of functions. Right? Like, you have a polynomial times a logarithm, right? Or you have like an exponential times a trig function, right? You have two very different kinds of functions such that a substitution isn't going to help you get out of it, but you have two different kinds of functions. So you have like an A and an L, or you have like an E and a T, right? In which you can apply Leote, right? So substitution is not going to work. What are my options? Well, if the thing you're looking at has two different kinds of functions, integration by parts is probably a good idea, right? Another situation where integration by parts would be a good idea to actually try out is if you have one function, but its derivative is easy to compute, and at the same time it would be convenient in an integral. Yeah. So I'm talking about an example like to integrate tangent inverse, right? You don't have a basic rule for that. Can't really simplify it to use a basic rule. Substitution, not going to get you anywhere. There's only one function, but surprisingly, integration by parts is going to be the nice thing to do here, because if you chose the u as the tan inverse, the du is 1 over 1 plus x squared. And that's something that's convenient, because it even looks like a basic rule right off the bat. Working with the 1 over 1 plus x squared is going to be more convenient than working with the arctangent. Right? Of course, your dv is going to be just dx, so that your v is going to be x. But ultimately, when you do the u times e minus the integral of v du is going to be x over 1 plus x squared, which a substitution can work on. Right? So integration by parts, particularly useful in these two situations. Of course, there are others. There are other useful situations. They're rare, though. For example, when we derived the integral of secant cubed, we actually used integration by parts, even though it doesn't fall into either of these categories. Right? Kind of falls into this category. You split it up as a secant and a secant squared, and the integral of secant squared happened to be very convenient. It's a nice tangent. You get rid of one of the powers. So integration by parts would be another option. Particularly useful if you're looking at an integral of two different kinds of functions multiplied together, or you're looking at a function whose derivative is more convenient than the function itself. Right? So like an arctangent or an arcsine, or just something where if I took the derivative, I'd know how to integrate that kind of deal. Right? So those are two situations which an integration by parts would probably be a good idea. Right. But again, you don't necessarily think of this fourth. You think of it when you see these two situations presenting themselves. Right? So the first three steps, you always think of those steps in that order, but in these two situations, you'd probably think, oh, integration by parts, assuming the first three steps didn't work out. Another technique, 5. we learned about the trig substitution. Right? So this is useful when expressions like x squared minus a squared, or x squared plus a squared, or a squared minus x squared appear, especially in radicals or in various situations. Right? So you have these guys and they're kind of like in this weird situation where I can't really do a substitution, it's not really gonna work out. So an example of an integral where you try a trig substitution would be something like x squared over the radical of 4 minus x squared. Now of course you'd think about a substitution at first, u equals 4 minus x squared, but your du is just gonna take off an x. And what's gonna happen to the x that's left over? It's gonna be this other huge radical, right? So the substitution isn't really going to finish the job here because you only have an x squared. Your du gets off one of them. So in this situation, what you would notice is that that 4 minus x squared, I can think of it as a squared minus x squared, where my a is 2. And a trig substitution can actually figure that out. Now, one thing I would note with the trig substitution is if a definite integral, right? Meaning you have numbers on here, always change the limits. Now in general with definite integrals, you have options. You can either change the limits and then plug in those numbers in the new variable, or you can keep the old limits, change back to the old variable after you've computed the integral, and then plug in the old numbers. Remember, for trig substitution, to change back to the old variable, you have to go through a whole process. You have to draw triangles, you might have to apply trig identities and stuff like that. That takes time. So if numbers are given here, actually just change the numbers into the theta variable and then apply that. Also note, don't apply if there is a positive odd power of x as a factor. Right? So, for this trig substitution, for this regular substitution, for this regular substitution, trig substitution on these guys is a waste of time. Okay? How? Because you have an odd power of x as a factor. Right? Once you have an odd power of x as a factor, a regular substitution is going to work out. The thing is, if you're, other than the thing you wanted to substitute, if the power of x that's there is an even power, that's when the trig substitution is going to be useful. Right? So, with these, substitution is what you would try. With this, your substitution isn't going to work, do a regular substitute, do a trig substitution. So that's when a trig substitution would be useful, and just some tips on actually applying them. So if it's a definite integral, I'm definitely going to change the limits so I don't have to draw triangles to switch back to the old variables. And if I have an odd power of x, sometimes this can also even work in the denominator, actually. I mean, I put the positive power because that's when it's easy to work out, but if this x cubed were in the denominator, you could actually still get it to work. It would put you in a situation where you'd need partial fractions though, which is the other technique. Partial fractions. So this is the sixth technique that we learned. When is this useful? This is useful if f of x is a proper rational function whose denominator factors or denominator factor, isn't it? Right? So if you have a ratio of two polynomials and you can factor the denominator and none of the other stuff works out, partial fractions is what you're going to choose, right? Of course, if it's not proper, you know to do the long division. Or I taught you the algebraic manipulation of trying to get the denominator in the power, then correct for the change that you made, split them up. You can do things like that. So some sort of algebraic manipulation. To get the expressions proper. Then you go through the process of partial fractions. You factor the denominator, you split it up into several fractions. The guy on top is 1 degree less than the guy on the bottom, in generic terms. If there's a repeated factor, you have to count up to the multiplicity of that factor, all that good stuff. I gave you the steps for partial fraction. So, if I'm in that situation, I would actually just do a partial fraction. So, notice that partial fractions could not work in this case because that is not a rational function because of the radical. If I didn't have the radical, then I probably would have thought of that as a partial fraction problem. So if I had, say, x squared over 4 minus x squared, instead of going through a trig sub, which tends to be annoying because I have to switch back to x, what I probably would do is something like factor out a negative, subtract 4 and add 4, break this up into two parts. That's going to be 1 plus 4 over x squared minus 4. And then I would have 1 plus, it's going to be x minus 2 over x plus 2. Use the cover-up method to find those guys, and Bob's your uncle, right? So here, I would use like a partial fraction. It's a rational function. The denominator factors easily. Not proper, but I can get around that pretty easily. And yeah, doing it that way is going to be easier than doing a partial fractions, having to draw the triangle and go back to x. Right? So that's the 6th technique that we learned. The 7th technique. This is the Weierstrass substitution. Right? So when is this useful? If f of x is a rational trig function and our trig identities are useless. Right? So, example, something like 1 over sine x plus cosine x plus 1 dx. I would use a Weierstrass substitution for that. It's a rational trig function, and it's not nice. Or sine squared over sine x plus cosine x plus 1. Also a rational trig function, and yeah, a substitution wouldn't be useful. Here you'd want to substitute the denominator, but the derivative of that is cosine x minus sine x. How are you going to get that to be useful? It's going to be hard to fit that in there. Similar with this. So your trig identities aren't really useful, but you can think of it as a rational trig function. Usually when you apply a Weierstrass substitution, it will put you in the partial fraction situation, which you can solve pretty easy, and then your variable is just the tangent of x over 2. If you can use, of course, if I saw something like sine of x over 15 plus cosine cubed of x dx, then I would use trig identities here, right? Because it would work. Like u is the denominator, u is cosine, and then my du would be the sine. So I'd use a trig identity. That would put me straight into a partial fraction situation, etc. So Yeah. So you're in a situation where you have a bunch of trig functions, but you can't really use a trig identity to dig your way out of it. Yeah, that's it. Those are the 7 fundamental techniques. So these are the fundamental techniques of integration. Now, you go into higher classes, especially in like complex analysis, you learn all of these crazy, in the cool way, crazy in a cool sense, techniques to do all these weird integrals that you couldn't even imagine doing them right now in some unimaginable circumstances. But at the end of the day, when it comes down to actually computing it, you're going to be doing one of these techniques that I told you. You're just going to have theorems to help you out to know that, oh, I can ignore certain pieces of this calculation, right? But at the end of the day, no matter how far you go into integration, at some point you're going to apply one of these rules that I told you. I told you all the fundamental techniques, the basic elementary techniques of integrations are these. If you really want to get minimalist about it, there are really only 2 types of integration, substitution and by parts. And all the other situations, they're just trying to get you into a situation where a substitution or by parts would be convenient. But that's basically it. So those are the 7 main integration strategies that, as long as you're alive and integrating stuff, they will be useful. And this is kind of when you would choose them. So again, the first 3 steps, always the same. Basic rule, can I simplify it to look like a basic rule? Can a substitution work? Always the first 3 things you would ask yourself. After that, if those don't work out, that's when you have other situations. Product of 2 different types of functions, integration by parts. If it's a rational function, partial fractions if the denominator are factors. If it's expression with x squared minus a squared, x squared plus a squared minus x squared, trig substitution would work if a substitution isn't going to work better, right? And rational trig function where my trig identities aren't going to help me out, I would use a Weierstrass substitution, right? So there's always a reason why you would choose a certain technique. It's not random, right? So a lot of times I'm asking for suggestions. You shouldn't be randomly throwing out suggestions. There should be a reason why you're choosing one technique over another. There's always going to be something in the problem itself that should hint to you, right? So I look at this. Of course, it's not a basic rule. Can't simplify it to look like a basic rule. Substitution is not going to work because my u is this. That x squared is going to give me trouble. A trig sub could work, but that's going to be kind of annoying. Partial fractions would work nicer because that's a rational function, so that's why, right? So my mind would go through that entire process, right? And ultimately, with a lot of practice, your mind should be able to go through this process relatively quickly, right? So it's really one of those, it's going to sound cheesy, but it's kind of one of those things where like the battle is won in the mind, right? Like the problem is dead before you even start writing, right? You look at this and within 5 seconds you should have a plan on how to kill that integral, right? The rest of it is just a formality so that I have something to grade. Better give Jhevon something to do, Like I know what the answer is, how it's going to work out, but Jhevon's going to be bored this weekend, so let me give him something to grade, right? So this is just a formality at this point. But you really should know how to actually judge an integral, how to come up with a plan of attack for an integral based on what you're seeing. Because, when I'm testing on it, I'm not going to give you any hints. I'm just saying, here are some integrals, do them. You're going to need to know how to do them. Did you have a question?
Yeah. Just out of curiosity, could you also do this question using trig substitution if you wanted?
If you wanted, it will be longer.
But it's possible.
If you did, what would the substitution be?
It would be the a squared minus x squared.
Yeah, but what is the substitution?
B sine.
Yeah, sine.
B sine.
Right, so you'd set x equals 2 sine theta. Right, you're going to get a trig function from that, which you have to solve first, then you're going to draw the triangle to figure out back in x's. To me, I think that's harder than this. But yeah. So you'll see that from time to time as well. Several methods can work for the integral that you're looking at. For example, we did the integral of secant in 2 completely different ways. And yeah, in general, I just pick the easier one. Trig sub tends to be harder than the other methods because the whole back substitution is a whole other process. You have to draw triangles and stuff. It's like a whole other thing. So if I'm like, well, I could do trig sub or I could do this thing, chances are the other thing is what you should do. So trig sub gets kind of sketchy there, but yeah, sometimes you don't have a choice. You got to do a trig sub. Okay, so now we have like 3 or 4 minutes left, which is more than enough time for the next section. We're going to play a game. Let's play a game. Pass these.
Yeah, I can.
There's more than enough for everybody. So.
Give me one more.
Yeah, we're missing one.
Here.
Ah,
Does everyone have one? Okay. So these are actually the exercises from a section in your textbook. So, but I just printed them out for the purposes of this exercise. And these are some printouts from another textbook.
Here you go.
It's also written by Stewart, by the way. Does everyone have one of these?
Nah, I don't have one.
There you go.
The one-page document?
Yes.
that one was one. Thank you.
These are the answers.
Okay. So, one of the lesser known tips in getting really good at math is to make a game out of it. I know it sounds kind of geeky, but I used to play a lot of math games when I was a kid. And one game that I like to play is, can I see the destiny of this integral within a few seconds? So that's what we're going to do. Go to the several page document. Okay, so I'm going to point out a random integral, and you guys are going to tell me how to attack that integral, and you have a 5-second time limit. Okay?
Okay.
All right. Problem 1, what would you do?
Trig ID.
Substitution.
Substitution, what would you substitute?
1 minus sine 1.
Good, okay. Problem 31. Okay, you guys are dead. Problem 32.
By parts.
By parts.
No.
How do you
do sub and then
Substitution, come on. Substitute u equals 3 over x.
Come on.
Problem 10.
Can you
Do sub.
substitution?
What would you substitute?
1 over x.
1 over x.
Good. Problem 11.
Trig.
trig sub.
What is the trig sub?
AC and x.
What is
X
a?
equals AC and x.
Okay, yeah. So when you answer, complete the answer. So you don't just say substitution, say I would substitute this. Right, okay.
It was,
Or,
what was it?
oh, it's a trig sub. X equals secant theta. Yeah. Trig sub could work there. A substitution could also work there, but you should be able to see that if I do a substitution, it would turn into a partial fractions problem. So you could also say that. I do a substitution, u squared equals the radical, u squared equals x squared minus 1. That's going to turn into a partial fractions. Right, so you could say that. 35. That's a trick question. Can anyone tell me the answer, the final answer?
It's tangent of cosine x.
No. Do you know the final answer?
Oh, finance.
Or tangent of cosine.
Pi over 2.
Because you need a sine to be that. You need sine x divided by 1 plus cosine squared for it to be an arctangent, right? Because you set your u equals cosine, your du would be the sine, you'd end up with 1 over 1 plus u squared. The trick there is that this is an odd function on a balanced integral. The integral is 0. Any odd function on a balanced integral is 0. How would you do problem 6?
By parts.
What would the parts be?
2x plus 1. Oh, okay.
Partial fractions.
I mean, yeah, that's what I meant. I don't know what I said. Partial fraction.
You meant partial fractions?
Yeah, I promise.
It's doable. Substitution would be nicer though. You could also do by parts. U equals x and dv equals 2x plus 1 to the minus 3. But a substitution is the easiest one to do there, actually.
Would you substitute?
You could do a partial fractions, but what would it look like if you do a partial fractions? You need like 3
Yeah,
fractions.
yeah.
You'd have to do a over 2x plus 1, b over 2x plus 1 squared, c over 2x plus 1 cubed. You multiply both sides by that denominator, you're going to have a lot of multiplying out to do. You're not going to have a lot of convenient numbers to plug in. Substitution, u equals 2x plus 1 can actually kill that integral. What about 7?
Substitution.
What would you substitute?
The y, arctan y.
U equals arctan y, yeah. What about 9?
Partial fraction.
Partial fractions, that factors. What about 36?
Substitution.
Substitution.
What would you substitute?
U equals sin x. U equals cosine x.
U equals 1 plus.
1
cosine.
plus.
Right, but there's a one, a plus
there's a
1
one.
there. So that's not gonna work.
Did you multiply the conjugate? No.
You can multiply and divide by 1 minus cosine x to get a sine squared in the denominator, split things up, and then you can do some u substitutions. What would you do with, let's see, 43?
Substitution.
What would you substitute?
U squared equals
Squared.
x. Oh, wait, no. Oh, wait,
Is that what you do, substitution?
U squared equals x.
You could do that. That's gonna put you into, like, you'd need to do a 1 over, 1 plus u to the 6th though. Do you know how to deal with that?
no.
What about problem 63?
Are you substitution?
You'd start out with a u substitution, u equals radical x, but of course you'll go into a situation where you need to by parts. By parts happens down the road. Yeah. So actually finish that up. Like get a partner and actually play this game. Maybe put a little skin in the game. You know? Okay, if I get more right, you buy lunch. Just make it fun. Like quiz people. Have a stopwatch the whole 9 yards. Can you see in 5 seconds what you would do here? So usually in like a test, when I give you like 4 integrals, I'm imagining you should be doing them in like, that's a 15-minute problem, right? However, knowing what to do takes you a few seconds. The 15 minutes is for you to just write it out, right? So practice doing that, just picking random integrals. Do you know how to do that in 3 seconds? Now the moment you can't identify what you would do, that's telling you, okay, you need to study the techniques and maybe go over what I did here to kind of see like, okay, really what would have worked here? And really get your intuition on point. Have some fun to do. Okay, we'll stop there. We'll pick up next Tuesday with partial fraction, with improper integrals is the next topic. But of course your test on, your quiz on Tuesday is just going to be on integration techniques.
Thank you.
Okay, all right, see ya.